Professor Koolen.
Good afternoon. All right.
So this is your last lecture.
Yes. Yes.
Thank you so much for giving these lectures. Even if
Okay, you're welcome. You're welcome.
Okay. So over to you, please.
So yesterday I introduced distance rally graphs. And maybe I should go back to the definitions. Yes. So distance rally graphs is when you have these AIs, BIs, and CIs. Yes. Then I give several examples. Yes. And then I give a list of examples. I think on this model there are 14 infinite families known with unbounded diameter, so something like this. So now I will start with primitivity because I want to introduce one nice problem. So what you need to do for that, you look at the gamma I graph. That means you take two further distance I, and that you call that the new adjacency, that is gamma I. So you join two vertices when they have distance I in gamma. And therefore gamma 1 is of course gamma back, and gamma 2 is the distance 2 graph, and so on. Yes, the distance I graph is this. And it's called imprimitive if one of them is not connected. So otherwise it's primitive. And this comes somehow from group theory. This is a notion that comes from group theory, but it is a combinatorial interpretation. So Smith showed that a distance graph with diameter at least 3 is imprimitive if and only if it is bipartite. That means the distance 2 graph is not connected, or antipodal. And in that case, the distance D graph is a disjoint union of cliques. Otherwise, the other, if the gamma 2 is not connected, then the gamma 4 is not connected, and gamma 6 and so on. All the even are then not connected. That is easy to see, but so the smallest is with 2. That is what I mean. So this is this. So a nice problem I will discuss now. All the known primitive distance graphs with diameter at least 9 are the polygons in the families I mentioned before, or related to the Hamming graphs or the so on. So you can have the halved cubes or the folded cubes and the folded halved cubes, and you can have the folded sums. That is what I mean by those graphs. And one nice problem is to classify the distance rally graph with large diameter. What is large? Maybe it is 9. That is my guess, but we don't know what is the right diameter to assume. And he conjectured that we know all the intersectionaries of the distance rally graph with large diameter. But he did not claim that he knows all the distance rally graph with large diameter. He only claims that all the intersectionaries are known. So, although the Twisting-Grassmann graphs were a big surprise to everybody at that moment, including ourselves, it is not a counterexample. It's not a family of counterexamples to Barnard's problem. That is what I said here. And I will now focus on the subproblem of Barnard's problem. namely when is a distance radius graph characterized by its intersection array. That means if I give the intersection array, if you give a distance radius graph with a certain intersection arrays, and then is the question, is this the only distance radius graph? Or can you determine all the possible distance radius graph with this intersection array? So now I will discuss the eigenvalues of a distance regular graph. So the lemma is, if I have a distance regular graph, then it is an eigenvalue of the graph gamma, if and only if it is an eigenvalue of this tridiagonal matrix. I put what I'm is a tridiagonal matrix. The rest is all zero. This two subdiagonals, they are all non-zero. On the main diagonal, there can be zeros and can be all positive numbers and non-negative numbers. But beside these three diagonals, there is only zeros. So I did not write anything there. So I hope that's okay. So there's a d plus 1 times d plus 1 matrix. How many different eigenvalues does it have? If you think in 5 seconds, you see if I add a constant times identity matrix to L gamma, that's still a tridiagonal matrix with the same BIs and the CIs on the two subdiagonals. But they are all non-zero. They are all positive. So that means that the rank is always at least D. So any eigenvalue of this matrix has multiplicity 1. So this matrix has exactly D plus 1 distinct eigenvalues. So that is what I say here. This implies that gamma has exactly D plus 1 distinct eigenvalues. Yes, and we can easily prove this. It's not difficult. So we showed this lemma last time when we were looking at partitions, equator partitions. So now if you have this collection of equator partitions that every vertex is a singleton in at least one of them, then we know all the eigenvalues of the graph gamma G. So how can we do this? How can we apply this lemma? So we know by the definition of this graph, this partition of the vertex set is an equator partition with quotient matrix L gamma for any vertex X of this graph gamma, yes? And this shows the lemma. Yes, because it has the singleton X. For every X we have this partition. Maybe I should have called it pi of X. Yes, then you see that you have many, for every X you have a pi of X. Yes, so that shows the lemma. So it is very easy. Yes. Now we define a standard sequence that satisfies this recurrence relation. And we assume that U0 is 1 and U minus 1 is 0 and UD plus 1 is 0. So we don't have BIs, BD plus 1, and we don't have C minus 1. So, and C0 is 0, yes. Okay, but we don't need C, we only need. Okay, we get this. So we call this a standard sequence or cosine sequence of 4 gamma corresponding to theta. And you easily can show that UI is a polynomial degree I in theta. Yes, was from the recurrence relation, yes? This is an easy induction. Okay, here's a little, okay. So we have in this graph with the usual kind of intersector array and with distinct eigenvalues k greater than theta 1 greater than theta d. We define EI is this matrix. Then EI times V, where V is an eigenvector for theta j. This is either 0 times V if j is not equal to I, or if j is I, then it's exactly V. So the matrix EI has only eigenvalues 0, 1, and there's only eigenvalues 1 for eigenvectors corresponding to theta I. And these EIs are called the primitive idempotence of gamma. So they are, we can also think them as orthogonal projections of the eigenspace onto the eigenspace of theta I. These are. So now A, B, A1. Then we have A times AI is BI minus 1 times AI minus 1 plus AI times AI plus CI plus 1 times AI plus 1. This is not difficult. You just look at XY and see then you see what happens. Yeah, if they are distance I minus 1, then you see that it must be B I minus 1 walks, and otherwise, and so on and so on. Yes, this is not difficult to prove. This means that AI is a polynomial of degree I in A. Now we look at the Bose-Mensah algebra. The algebra, we can also call the adjacency algebra, or in particular case for a distance vector graph, the Bose-Mensah algebra is equal to the adjacency algebra. It's the algebra generated by the matrix A. What that means is these are all polynomials A. The algebra where you only look at polynomials in A with real coefficients. So on one hand, this would be 0, yes. This product is 0, yes. Because if I do any eigenvector, that gets 0. So this shows that there's a polynomial of degree D that is 0. This means that the dimension is at most D plus 1. Do I not make a mistake here? This is D. Oh, this is D plus 1. Yes, so this is a polynomial of D plus 1 of degree D plus 1 that is finished. Yes. And this shows that the Bose-Mensah algebra has dimension at most D plus 1. And clearly, the AIs are all linear independent, yes? Because they have zeros and ones in completely different places, yes? The ones are all in completely different places, so they add up to the O1 matrix, yes? So they are clearly linear independent. So we have D plus 1 linear independent elements in our algebra, and they are all that we have already shown. Okay, so also the primitive idempotence EI are also linear independent, because EI times EJ is delta IJ EI. So they are EI times EJ is 0 if I is not J, and EI squared is EI. So we can write EI as a linear combination of the HAs. Yes. And the rank of EI is equal to the multiplicity of theta I. So we call them MI. The second thing is that EI has constant diagonal. And the third thing is because EI has only eigenvalue 0, 1, the rank of EI is equal to the trace of EI. It's the number of ones on the so the rank of EI is the number of ones as eigenvalue. And that is exactly the same as the trace of EI. We see that alpha I0 is mi over n, where n is the number of vertices of gamma. And we also see that AI is the sum I0 to d e theta I EI. If you multiply both sides by EI, then you see that we know that AEI must be delta EI. Yes, that we know. So we get this. We also have this. So if we have now the standard sequence with respect to theta I, then it's easy to see that alpha IJ is alpha I0 times UI, because the EIs are constant on the HJs, yes? So that is what we have above, and therefore we must have, essentially they are eigenvectors of the equator partition gamma x, gamma 1x, gamma 2x, and so on. Yes, that is what follows. And the standard sequence gives us the standard representation. What does that mean? What I mean by this? So we have a theta, an eigenvalue of gamma, and we have the standard sequence UIs. Then there exists a map from the vertex set of gamma to the Euclidean space of dimension m for some positive integer m, such that the inner product sigma x, sigma y is exactly u, the distance between x and y, for all x and y in phi gamma. And we can take m to be equal to the multiplicity of theta. I can show, do I have enough time to show it? I will skip the proof, but it will be in the slides. So it's not difficult to prove this, but I think it's better that I go to other things now. But so this map sigma is called the standard representation of gamma with respect to theta. And the standard representation is a reason for reason of cosine sequence, as the UIs must lie between 1 and -1. So we can think of them as in cosines of a certain angle. So now we give that proof I will skip. So I'm sorry. Oh yeah, now I can look at Big's formula. So the big formula can also prove easily. You only use the fact that EI squared is equal to EI. If you look at this equation, then you can show the big formula. Because you have in principle already everything is set up to prove this. So this gives so you don't have to know the distance radiograph to calculate the multiplicities of your distance radiograph. If it does exist, then these are the multiplicities. But if the multiplicities are not integer, then the distance radiograph cannot exist. If the multiplicities are negative, the distance radiograph cannot exist. So that gives a very strong feasibility condition. So this is a very strong condition that the theta, the multiplicity of theta must be always positive integers. And you can say a little bit more, but I'm not, that is not so important now. So here are some remarks about Big's formula. So this multiplicity of theta is a rational function theta, and hence is almost everywhere continuous. This was important in the proof for the binary ether conjecture. The multiplicity are positive integers. This is a strong condition I already said. And t-diagonal matrices are somehow one-to-one corresponding to the orthogonal polynomials. So the theory of orthogonal polynomials is exactly the same as the theory for three-diagonal matrices with positive subdiagonals. So now I will look at the Hamming graphs. And what I'm going to present is due to Terwilliger, and it was shown by him in the early 1980s. He claimed that he did this in the evening for his job interview, and he talked about this result the next day in his job interview. So BCN is a book, Brouwer, Cohen, Neumeier, and it's called Dieselberg. It's published by Springer in 1989. So I will first show an upper bound for the second last eigenvalue of a Dieselberg graph when it contains an induced quadrangle. So the lemma is as follows. If you have this graph with an induced quadrangle, then the second last eigenvalue is at most B1 minus 1. And if you have B1 minus 1, then you can say much more. And we shall see that you can, in principle, classify them all. So how do you prove this? It's not difficult. You will see it is amazing trivial. I mean, so you take an induced quadrangle, say x, I say it to u, I say it to y, I say it to w, I say it to x. Yes. And let the ui be the standard sequence with respect to theta 1, and sigma the standard representation with respect to theta 1. Now you consider this very complicated inner product. Yes? That is sigma x to sigma y, the opposite minus the other two opposites. Yes? With itself. So we know that P has to be at least 0. Yeah? Then you can also calculate it's 4 times U0 plus U2 plus 2U1. And with a little bit calculation, you can see that theta 1 is, this is equivalent with theta 1 is at most B1 minus 1. Yeah, this is not difficult, you can do it yourself. So this is an easy exercise. And if theta 1 is B1 minus 1, then P must be equal to 0, yes? That means that sigma x plus sigma y should be equal to sigma u plus sigma w. Yes? Very good, yes? So now you take a vertex set that is a distance I minus 1 from x and distance I plus 1 from y, and therefore the distance between u and z and w and z is I. For some I is 1, 2, 3, and so on. And now you assume that B1 minus 1 is your second last eigenvalue. Then you can calculate ui minus 1 plus ui plus 1 is sigma x, yes, sigma z, with inner products sigma x and sigma y. But that is also because sigma x plus sigma y is sigma u plus sigma w of phi. Oh, I'm making a mistake. I meant phi z. My w and my ph's are the same. I'm sorry. And this completes the proof. Yeah. So this is so good and so not so difficult. Yes. So this lemma, you see that if you have induced quadrangle and theta 1 is b1 minus 1, then you have a very nice expression for your standard sequence. And this is very easy to prove. We do it by induction on I. For I, it is A0, it is clear as U0 is 1. Then U1 is theta 1 over K. That P1 minus 1 over K is K minus A1 minus 1 minus 1. B1 is K minus A1 minus 1 because C1 is 1. And then you have to subtract a 1. So you get, so that is 1 minus A1 plus 2 over K. Yes? And then you easily do your induction, and then you get it, that you have the right expression for ui plus 1. So now I will follow PCN section 3.14 and 3.15. So this is about root representations and root graphs. So a root representation is a map from the vertex set to the Euclidean space of dimension m, such that if I look at for two vertices x and y, I look at tau x minus tau y in a product with itself. That's always even. And it's equal to 2i if I is at most 2. We don't require anything else. And it's strict if that only happens for the first two. I mean, that the tau x minus tau y with itself is a mod 4, even only if the distance between x and y is a most 2. It is 2 if the distance is 1 and 4 if the distance is 2. And a root graph is a connected graph that has a root representation, and a strict root graph is with a strict root representation. Yes? And now, now is your question. Why do you call it a root graph? Yeah, I'm not going to go into details here, but now you go to lattices as this is not a partial order set. This is something generated by a finite number. The integral they have the same name. I'm sorry. That's how it is. But this is the reason for the root name root graph. And it's not so difficult to see the foreign lemma. And in connected graph with small eigenvalue minus 2 is always a root graph. And a regular root graph of diameter most 2 has always small eigenvalue minus 2, at least minus 2. So So this is not difficult. This is, you can take it as homework. So in this sense, good graphs generalize graphs with smallest eigenvalue at least -2. And there are many examples of good graphs. You have the Hamming graph, the Doob graph, the Johnson graph, the half cubes. This is the two graph of the hypercube and the icosahedron, for example. But you have many more. Not so many more. You have only one more, I think. Sorry. Unless you are. Yes, you have only a few more. You have quite. You have at least. No, there are several more. Yes, there's an infinite family that I didn't mention, but that is not an infinite family of distance graph. It is a family by Brouwer and myself that we found. But I will discuss this later anyway. So these are examples of good graphs, and they are all strict good graphs. So now I have to define amply regular. That means it is only locally distant regular. That's somehow you can say it. A graph that is somehow locally distant regular. Whatever that may mean. So what do I mean in this way? The valency is K. Any two Archean inverter have exactly A common neighbors, and any two inverters at distance 2 have exactly C common neighbors. So we don't require anything else. We don't require much, yes? So now I might classify the amply regular good graph with C at least 3. You can see, for example, BGN theorem 3.15.1. But in 3.15.1, they claim a more general result. And this result is not correct, as there exists another infinite family of good graphs with C is 4. And this is also amply regular. This is not amply regular, but they are regular, and they are, the CIs always exist. That is what the uniform geodetic means. And I will not tell you what is code graph, but that is a special case of a good graph. And the paper is published in 1993 in Discrete Mathematics, when I was still a PhD student, I believe, yes. Okay. So in 3.15.1 and 3.15.2, we have a complete classification of amply regular root graphs with parameter C at least 3. And then you get the cocktail party graphs. C is 10 and gamma is the COMSATS graph. C is 8 and it is the Clefley graph. And the other C is 6 and you get a half cube. And C is 4, you get the Johnson graph. And the 3 Chang graphs, they have the same parameters as Johnson 8.2. There are 3 of them. There are 3 exceptions. I'm a little bit early. Before CS2, we need the strict root graph condition. This is not true if you don't have the strict root graph condition. I will discuss it a little bit later. Let gamma be a complete, non-complete amply regular strict root graph with parameter CS2, then it is a Hamming graph, or A is equal to 2, and gamma is a Cartesian product of 4 click strict Hamming graphs and icosahedrons. So so it is a Cartesian product of many different, these 3 different graphs. You can have 100 copies of 4 click 3 copies of stick-counter graph and 5 copies of icosahedron, then you get an example. So that is the theorem, that is what they showed in 3.15.4 in BCN. And if we remove the condition strict root graph, then this theorem is not correct. This was shown by Brouwer, Klin, and myself. We gave an example of that is locally the line graph of the Peter graph, of a strictly root graph that is locally the line graph of the Peter graph that has C is 2 and is amply regular because the line graph of the Peter graph is regular. Now we come back to this graph with an induced quadrangle having second last eigenvalue θ1 equal b1 minus 1. So we first show that such a distance graph must be a strict root graph. And this is almost trivial. Yes, you look at this. So you see that this is 2 times the distance between x and y times a1 plus 2 over k. So we can now multiply everything by square root k over square root of a1 plus 2. Then we get 2 distance xy, yes. So if you make tau this number, then yes, then you see that we get a strict root representation of those distance graphs. So they are strict root graphs. So we have then the following result by Terwilliger. And it is, for example, 4.4.11. In 4.4.11, they have also a case when there is no quadrangle, or the C2 is 1, or distance, the diameter is 2. They have more cases in there, but if you only look at the induced quadrangle with diameter at least 3, you get the following. So you get C is 2, and it is Hamming or Duke graph. It is C is 4, and it is a Johnson graph. For diameter 2, you get also Chang graph. And C2 is 6, and it's half cube. And for C2 is 8, you will get Schlepper graph, but there's also diameter 2. And for C2 is 10, you get the COMSATS graph. So there's no contradiction with what I said before. So this says that the Hamming graphs and the Johnson graph are essentially characterized by their intersection rate. I will not discuss the other graphs today. For the Grassmann graph, it's almost, they are almost always characterized by their intersection array, except for the Johnson Q, JQ, 2D plus 1D. Then we have the same parameters as the twisted Grassmann graphs, and nobody knows whether there are other graphs with this, other distance Hadley graph with these same parameters. This is a very big open problem. For the bilinear forms graphs, quite a bit is done, but not completely. There's still a lot of work to be done for the bilinear forms graphs. But this is where I'm going to stop today. Thank you for your attention for the whole week. It was a pleasure to give these lectures to me. Thank you so much.